Okay, let's take a quick look at some important free radical reactions. If we look at the halogenation of alkanes, then we normally do this with the halogen, either chlorine or bromine, and we need some kind of source of energy. So if we just mix an alkane like methane and chlorine together in the dark at reasonable temperatures, then absolutely nothing happens. However, if we shine a light on the reaction, then we all of a sudden start to get chlorinated hydrocarbons, haloalkanes. Overall, the reaction is a substitution because we're taking some of the hydrogens from methane and replacing them with chlorine atoms. So that's a substitution reaction. We've swapped a hydrogen for a chlorine. So how do these reactions work? Well, they're free radical reactions, and they're a type of free radical reaction called a free radical chain reaction. So free radical chain reactions have three different types of steps in the mechanism. There's initiation, there's propagation, and there's termination. Initiation steps take non-free radical species and turn them into free radicals. So remember, free radicals are species that have an unpaired electron. So if we take chlorine and shine light on it or heat it enough, then we'll get chlorine radicals produced. In fact, we'll get two as we break that bond in what we call a homolytic bond cleavage. So homolytic comes from the words homo, meaning same, and lysis, meaning to cleave. So it's the cleavage of a bond in an equal way, where one electron goes to one half of the molecule and one electron goes to the other half. And that's as opposed to heterolytic bond cleavage, where the electrons both go to one of the two species. So free radical reactions then involve a propagation step. So propagation involves new reactions which generate other radicals. So we take radicals on the left-hand side of the equation and we end up with radicals on the right-hand side. So a chlorine radical reacting with methane gives hydrogen chloride and a methyl radical. The methyl radical in a separate step then can react with chlorine and produce chloromethane and a chlorine radical. The final step of a free radical chain reaction is the termination step. So termination is where we take radical species and we combine them with other radical species and we produce non-radicals. Okay, so it's termination because it's stopping this chain propagation of the reaction. So we get free radicals forming neutral molecular species with no unpaired electrons. So methyl combining with methyl will give the ethane molecule, and a methyl radical combining with the chlorine radical will give chloromethane. We also have one more, which is the chlorine radical combining with another chlorine radical to make chlorine Cl2, the chlorine molecule. Okay, so given the choice of different places around an alkane to react, free radical halogenations are usually selective to some extent. So they will generally give halogenation at the more substituted position. So a primary alkyl group, like this position here, is less reactive than a secondary alkyl group, like this one here. And that is less reactive than a tertiary alkyl position. So the reactivity increases the more substituents we have on the carbon undergoing the halogenation. Radical chlorinations are not normally that useful. Industrially, they're useful to make bulk chemicals that include chlorine, but they're not very selective, and so we don't generally use them in an organic chemistry lab to make a particular molecule. The reason why we get this selectivity is because the radicals that we form are more stable with the more substituents on the carbon that bears the radical, that unpaired electron. So methyl radicals are extremely unstable, primary are slightly more stable, secondary are more stable still, and then tertiary radicals are the most stable. And so tertiary radicals are most easily formed, and therefore the halogenation happens most easily at tertiary positions. A side product of this is that we can sometimes get optical isomers out of these reactions depending on which of the hydrogens from a molecule are replaced with a halogen. So if we halogenate this particular compound, then we'll end up with a new chiral center, and that can be either S or R. Now, just as a little aside, free radical chemistry is extremely important, particularly in formation of polymers. So a lot of polymers are formed through free radical polymerization, and it's used to make a huge number of polymers, particularly things like polystyrene. So polystyrene can be made through a free radical polymerization, where we take a phenyl radical and it adds to styrene, and we end up with this structure here that then adds to another styrene molecule. So these should be single-headed arrows like that, and we build up this polystyrene chain. And I'm sure you've seen polystyrene used in lots of different applications, including as a packaging material. Okay, so hopefully that gives you a little bit of an overview of radical chlorinations and halogenations, and also a little bit of insight into free radical polymerizations. Thanks for watching.